6, functions defined by tables and graphs. We're going to be working with this idea of functions for the next couple lessons. A function is a specific type of equation in math. And I'll tell you that the equations we've been doing, for example, slope-intercept form, those are functions. So that's kind of an example of one of the ways a function might look. Now, this is by tables and graphs. If we were doing it with, say, equations, you don't need to write this down, but I'll just put it in here. When we had slope-intercept form, when I plugged in one value for x, how many answers did I get for y? I plug in one value for x. Let's say I pick a number for x. Let's say you were going to make a chart even. If it wasn't slope-intercept form, but just an equation that you were going to graph. You pick one value for x. How many answers do you get for that one value? It's not a trick question. Diego, 1, right? You pick one value for x, you plug it in, you get out one answer for y. That's essentially what a function is. So, in terms of the definition, a function means that if you have one input, so you put one value in, you have only one output, only one possible answer. I'll show you some examples here in a second. There's going to be a little bit of writing for the notes today. The good news is that for your homework, you don't have to do a lot of math. There's going to be a little more of writing charts because this says tables and graphs. This would be using an equation. We're going to be doing functions with equations, I believe, tomorrow. But for today, we're going to be doing tables and graphs. So, for example, there's an example in your book about birthdays. George Washington had one birthday, February 22nd. Pretty close to today, which is why we had yesterday as a holiday, President's Day. Well, it wasn't just him, it was also Abraham Lincoln. He only had one birthday, February 12th, right? One input. Now, here's the idea. The input, this isn't a number, right? It's not like we're picking a value, but it's sort of like the first piece of information. If we're looking at a table or a graph, the input, instead of plugging a value in for x, like if we were making a chart to graph, the input has a special name. It is called domain. The output, the answer, now again, it's not like you're doing any math. If we were doing this, you would just be looking at information on birthdays. You don't have to do anything. The output, the answer you get, is called the range. Now I'll come back to the birthdays in just a second. Think about this. If this was our chart where we were plugging in, the input, the value we picked for x is the domain. The output, or the range, would be the value we get for y. Is it possible for a domain, in this situation that I'm showing you, the example of birthdays, is it possible to have more than one range, more than one output? Can you have more than one birthday? No, you're born on one day. It's not possible. So that's why they're using this example. If I talked about your height, right now, today, can you have more than one height? Really? If I measure you right now, and then I measure you a second time, it's going to be two different numbers? No. Nobody in here grows that fast. Not even you. Nobody. We have one height. If I asked your age, you have one range, one output. You can't have more than one. I'll give you an example in a minute of something where you could have more than one and why that wouldn't be a function. But the idea here, oh, by the way, Abraham Lincoln, right? So this is why we just celebrated President's Day. Their birthdays were pretty close together. We celebrate them both on one day, and that was our holiday yesterday. But what if somebody, I'll put his first name, what if somebody had the same birthday as one of these people? Charles Darwin, also was born on February 12th. He shares a birthday with Abe Lincoln. And then we'll put in one more person. Let's get a famous woman in there. Marie Curie, famous scientist. She discovered radiation. So if you've ever had an X-ray, that's thanks to Marie Curie. Okay. For each one input, there's only one output. Even if the output is the same, even if the range is the same. So Darwin and Lincoln can have the same birthday, but for each one input, for each domain, there's only one range. Think about it if we were going to graph. If you plugged in a value for x and you got a bunch of different numbers for y, you would not get a straight line. You're going to get all sorts of crazy stuff. The idea with this is just looking at data instead of graphs. Or instead of straight line graphs, excuse me. Now, what if we were going to plot this? Remember I said the domain, the input, let's also call that our x, and our output would be like our y value. So again, the idea of if we were plugging it in, making that chart to graph it. If I said, list these as ordered pairs, you could abbreviate GW 222, Abe 212. I'm abbreviating a little bit to show you that because although you're going to be writing words, you can abbreviate a little. Charles Darwin, that's my x value, my y value again. Now, 212, well, that's not exactly a point on a graph, but we could have it be months. But if you're asked to put it in ordered pairs, A, you can abbreviate, and B, think about x and y. X is your input or your domain, y is your output or your range. And so you're just listing that, because we could make this a graph. In this example, we're not going to graph it, but I'll show you on the next one how we would. Okay. Next example. Instead of like that, maybe we have a chart where we have different kinds of trees and their height in feet. So let's say the oak tree out in the yard, we don't have one, but if we did, and we measured it and it was 25 feet. And we had a poplar tree, and it was taller. Could there be more than one output? No, there can only be one height per tree. Let's get one more up there. Let's say a juniper. Those are often shorter, sometimes even more trimmed down to be more of like a hedge. Okay, I'm just going to do 3. Your book gives more examples, but I'm trying to shorten it up here. Could you make this into a graph? And if so, what kind of graph would you do? Luke?
Bar graph?
Okay, you have 2 choices of graphs that you're going to see today. A bar graph would be a good choice. Any other kind that you might make? You could also do a line graph. So real quickly, I'm going to review that. What you guys are going to be doing today is working mainly on either, I'll put this back up in a second, either looking at a table like this and putting it into ordered pairs, x and y, domain and range, or you're going to be looking at a table like this and deciding what kind of graph to make. Often for a line graph, we do that to show a change over time, over a period of time. In this case, the trees and the height, there's no time involved, so maybe a bar graph would be best. I'm just going to show you a couple things about graphing that I need you to remember, and then we can plot that if you'd like. First of all, whether it is a line graph or a bar graph, you must label. So let's say we're going to do the tree one and we're going to do a bar graph. Okay? You would say trees, and you would say height, And because this height is being measured in feet, you need to say that. It's not inches, it's not centimeters. So first of all, so we'll do this graph, and what I'm going to do here in orange is just list the parts that you need to have. Labels. So you need to say what it is we're looking at. You should also have a title. Height of trees or something. In some cases, the title will be given to you in the little chart. In some cases, you might need to just make up a title that matches the information. So you need to put your labels on it. Generally, you're going to want to do numbers on this y-axis, unless it's a line graph. Then you want time on the bottom. So let me just do over here for a line graph. I'm not going to show all the same labels, but on a line graph, you always want to have time on the x-axis, no matter what. And don't forget on a line graph to connect the dots. When you plot each point, it shouldn't just be a bunch of points. It's not called a bunch of points graph. It's called a line graph because it should form. It might not be a straight line. It might go up and down. Okay? Now, the other thing that you need to do is you need to figure out the scale where there's numbers. For trees, well, there's no scale, but you need to label each item. So we had oak, poplar, and juniper. And I'll give you graph paper for this so that it's nice and neat. So you need to put the information. Now, on the numbers here for the height, when we decide the numbers, that's called the scale of the graph. We need to decide what numbers make sense. If I had each line be 1, 2, 3, 4, 5, well, I look at this, I need to go up to 30 for poplar. I don't want to have it be that big. So my smallest number is 10, and my biggest number is 30. Any suggestions for scale? Roland? Maybe by 5s. I think that sounds good. If we start at 0, 5, 10, 15, 20, 25, 30. Now the idea for scale is you want 5 to 10 items. If it's less than 5, let's say you went, oh, let's go up by 20s. Oh, 20, 40, 60, we're already too high. We don't have enough items on the scale. If you said, let's go by 2s, oh, 2, 4, 6, oh, it's going to take too long to get to 30. You only want 5 to 10 items, meaning numbers, on the left side here. So you have to decide what's the right interval. It has to increase by the same amount each time. Now, for the bars, in a bar graph, straight lines, I'm writing here not what it's going to look like, but what I need you to include. Straight lines. Use a ruler. Don't freehand it. And space between the bars. If there's no space in between, it's a different kind of graph. It's called a histogram. So, for example, on the oak tree, at 25 feet, now I don't have my ruler out and I'm not on graph paper, so I'm estimating, try to make it kind of straight there. On a poplar tree, 30 feet, now I'm going to go up into my words here, but I leave a little space in between. Now if this was on the graph paper, I would suggest use the lines of the graph paper. Have these be the same width. They should maybe each one row of squares, one column. Maybe in between you have one empty column of squares, one row. Just make it look all the same. Okay, and then juniper was 10. Here's what I don't want. Hopefully that one looks worse than the first two. I tried to make it look bad. You think I won't notice when you freehand it? I will notice. Make it straight, make it neat. If this were a line graph, we would have our dots and we would connect them to make a line graph. I'm not going to graph this one. That's really all we're focusing on here. Let me just show you, for example, a line graph. This is an example from your book. It talks about population in the millions. So first of all, United States population. Population in millions. Don't tell me that in 1980 there were 227 people in the United States. That's ridiculous. There were 227 million people. So we do need to say that we're in millions here. Notice here they went up by 25 for each. What you want to do for your scale is look at the smallest and the biggest number. Here, but from 76 to 227. So we kind of know how much we need to show. So remember a line graph, you're just connecting the dots. It doesn't have arrows at either end. It doesn't go continuously. And we also don't know which direction. Maybe it starts to go down. Notice this is not a straight line. Okay? So, all you're going to be doing today is that. Nothing too difficult, just introducing the idea of function.